delta function. All right. Now, let me just explain something about this. It can be called a Dirac delta function. It can be called an impulse function. This is a different one. It says dry erase. The symbol for it is delta of t. That's all it is. Now, here's what it is, though. This is for continuous time. We're doing all continuous time now. Delta t is basically this. If you take a function, say this is t, and this is 0, and this is going to be the vertical dimension, delta t. If you take something like this, where the height of this, all right, is going to be 1 over delta t, and the width of it is delta t, you'll notice that the area under there is 1. So for this delta function that has height 1 over delta t and width delta t, the first thing you notice is the area under this thing is 1. What the function is, by definition, delta t is equal to the limit as delta t approaches 0 of this function. Just use this as a drawing. You all see that here? That's the delta function. It has a height going to what? As delta t goes to 0, what's the height going to? Infinity. What's the width going to? 0. So I call it a spike. It looks like a spike. That's all it is. It represents an approximation for things that we can actually generate. That's a delta t. All right? Now, the interesting thing about the delta t, I just mentioned it, is if you integrate delta t dt, really from minus infinity to infinity, you get 1. The area under the curve is 1, correct? I'm going to go a step further. I don't have to start at minus infinity and go to infinity. I can say if I integrate from minus epsilon to plus epsilon, where epsilon is approaching 0, of delta t dt, it's 1 as well. That's very important. All right? I'm going to show you the next property of the delta function that's real important. Getting a handle on that? It's just a spike. That's all it is. But it's going to be useful. Now here's why it's important. If I integrate, now pay attention to this, I integrate a function, and I take delta of t minus tau, right, times any function f of t dt, I'm going to do the integral from minus infinity to infinity. I want you to think for a second now. Where does this delta function turn on? Where does the spike occur? Look here. The spike occurs when what? When t is 0. You all see that? Everybody see that? At t equals 0 is where you get an infinite height and an infinitesimally small width. You all see that? Now, it means the argument here, whatever is there, that in this case it's t, when that argument goes to 0, that delta function, I say, turns on. Do you all see that, class? Are with me? Now we're going to evaluate this integration. All right, now when I look at this integration, delta of t minus tau is 0 almost everywhere except where what? Where t what? Where t minus tau equals 0. Correct, class? Isn't that right? And where is that point? Where t is equal to tau. Correct, class? Now, keep watching. If that's the case, I'm going to say that really what this looks like is the integral, right? From, since it's tau, I can say from tau minus epsilon to tau plus epsilon, where tau is now going, where I should say where epsilon, pardon me, where epsilon is approaching 0 here, of the function delta of t minus tau times f of t dt. Do you all agree this is basically the same thing? Because now I'm just focused on that small portion of the actual integration where the delta function will be on. Do you all see that? How many do? Right here? Well, you understand the epsilon is just something that is going to become very small and approach 0, right? So you're really going from what? You're going from a little bit below tau to a little bit above tau. You all see that? Now, having said that, I can say that this f of t itself doesn't change much from here to here. It's going to have about the same value here as it would here if these two values are just about indistinguishable. Do you all grant me that? So I can say that this integral will really look like f of tau times the integral of delta of t minus tau from tau minus epsilon to tau plus epsilon dt. You all with me on that, class? Can you all see it okay? And what is this integral? 1. This is called the sifting property. Therefore, this integration is simply f of tau. This is called the sifting property. In other words, if you have any function, if I have any function f of t or g of t or whatever, times delta of t minus tau d tau, from minus infinity to infinity, it simply extracts the value of the function f of t where the delta function turns on. It comes out as simply f of tau. You all see that, class? You're wondering why that's so important. It will become apparent later. Got that? That's sifting property of the delta function. And it should make sense to you. Now that's the delta function. The next function we talk about is actually the integral of the delta function. All right? That's delta t. Did anybody have delta t before? Kronecker delta functions in math? Anybody? You had them Kronecker delta? What course? Calc?
No, mine.
It's delta function. Which course did you have it in?
I've seen in physics.
Physics.
Yeah, quantum.
Next stage to law and maybe
Oh, you had this already. Okay. Where are you from? What?
Italy.
Italy. I had 2 Italians. They were from Rome last time. Strange Fratelli's is a restaurant up here. And we got guys from Rome who are actually running. Do you know Fratelli's is Italy? Who does? Your head's shaking. You do? It's a great restaurant. Strange. So we got another Italian graduate or Italian exchange student. Welcome. All right. Now, the delta function is important, but the next function is called the step function, or it's called sometimes just, I'll call it the step function. I guess there's a lot of things for it. It's u of t. And I'm going to draw what it looks like. But u of t is the integral of the delta function. It's the integral from minus infinity to t of delta t dt. Now just think about that for a second, what that implies. If I take a look at a delta function, right? I'm just going to show you what I mean. If this is delta t, this is the way we actually draw delta t versus t. We put a little arrow at the top of a line, and that's the symbol for delta t. That's it. But if I take this and I integrate it, really I'm taking a look at the area under the curve, am I not, as I go? So down here, if I plot the integral from minus infinity to t of delta t dt, if this is what it is, u of t, if I plot this, then I get 0 until I hit this point where the delta function goes to infinity, and then I have a value of 1 after that. Do you all see that? So sometimes this is called a step function, u of t. It's really used to represent switching. If you think about, if you wanted to get something, remember when you had circuits? You always have a battery, and then you have a switch for the RC stuff and the LC, and you throw the switch, right? Well, mathematically, the way you can represent that is simply u of t, and the weight of the voltage would just be like 12 volts u of t, would represent a battery and a switch mathematically. Does that make sense to everybody? Let me just show you how come u of t is so useful. Suppose this is the old way of doing business. 12 volts and a switch like this. It goes down to t equals 0, and this connects to the circuit, right? Y'all remember seeing that, right? Then you'd have an L and a C and an R and a C or something like that. Well, why do it that way? Mathematically, this is an easier way to do it and also serves a purpose when we do analysis. We could just put plus to minus 12 u of t here and then connect that up. No switch, no battery, no problem. Got that, class? So this is one reason we use u of t. You'll see more. It becomes important. Just to give perspective. But u of t, from a practical standpoint, is the integration of the delta function. Follow me? That's it. And what would, here's a question. You'll notice u of t really is what? It turns on, or goes from 0 to 1 when the argument of t is 0, right? The argument where t is 0, correct? Well, what does this look like? Suppose I had u of t minus, say, 20. And this is t. I want to know what u of t minus 20 looks like here. What does it look like? I know whenever this argument, right, is less than 0, it's 0, correct? Y'all with me? So it's 0, 0, 0, 0, 0 until I hit 20, and then it's 1, 1, 1, 1, 1 forever. Got that? What would happen if, just write it down. I know people are copying everything. I used to do that. Y'all got that though? Now here's the next part. What does it look like if this is the case? I'm going to erase this. I cheat. I can do this very easily. U of t plus 20.
It'll start at negative 20.
She's right. Y'all hear that? You first look at where it's 0. T plus 20 equals 0. T would be minus 20, right? That's where the transition takes place. Y'all agree with that? So I come down here to minus 20. I know that's where transitions. Then go a little lower than that. What if t is equal to minus 21? Minus 21 plus 20 is minus 1. U of minus 1 is 0, right? Matter of fact, the formal definition for u of t, if you want a good one, there's so many, u of t really is equal to 1 for t greater than or equal to 0, and it's equal to 0 for t less than 0. That's another mathematical definition. There's so many. The integral definition I used is acceptable, but the idea is get it in your mind, u of t is either 1 or 0. And it's 1 whenever the argument's positive, or 0, and it's 0 whenever that argument is negative. Are you with me? How many see this right here? Make sure I'm getting to everybody. All right. Now that's u of t. The next function is this one. This is a good one. It's called a ramp function. This is called a ramp function. All right? The symbol for the ramp function is r of t. And here's what a ramp function looks like, and then I'll show you what it mathematically is. This is r of t. It simply has a slope of 1. Here it's t, and it's 0 here. So it's really what? It's 0, then boom, comes up at an angle of 45 degrees, or with height, really, this is equal to this in terms of the value. Take any value of t, that's the value of r of t. Do you all see that? A mathematical way of saying what r of t is simply t times u of t. Are you with me? And really what r of t is meant to be is equal to the integral from minus infinity to t of u of t dt. If you think about that, u of t is 0 for any arguments of t less than 0, right? So if you integrate 0, 0. Then what do I hit? When t is equal to 0 greater than that, I have 1, right? The integral of 1 dt is t, correct? So then I have simply t. But the u of t you have to put here so it keeps your head on straight. You'll know that you just don't have a function t. The function t looks like this, doesn't it? Right? So we got to get rid of that, and that's how come you put a u of t there. That's the ramp function. Ramp function is an integration. And you'll see this is also very useful in describing mathematically functions that we'll be using. Are you with me, class, so far? So you got 3 new functions. You got the delta, the ramp, or really the delta, u of t, and the ramp. I'm in continuous time. Now they have discrete time analogs, and I'll show you in a bit. All right, I want to focus on continuous time for now. So what do we use these for? And I'm assuming you're familiar with sine, cosine, and things like that. There could be one other function I give you. Don't know if I want to do it now. Yeah, I'll do it. Sometimes I regret doing this. You all got these down, right? Feeling comfortable? There's one I like calling it a pulse function. The book uses something called a rect function. Write this down. The book uses RECT, and then it's T over tau. Please put this down. That's the same thing as the way I like doing it, called the pulse function, P tau of T. I'll show you what they are in a second. So when I look at this function right here, here's what it looks like. I can state it mathematically many different ways. This is the pulse function of t, which is the same thing as the rect function t over tau. Does anybody have this? Rect of t or pulse t? Anybody? Well, you probably had this. You've seen it? You haven't seen this function? This is the same thing. If you want, how many different ways could we express this? You'll notice the width is tau on this one, class. Do you all see that? The width is tau, the height is 1. That's the key thing. It's centered at the point t equals 0, or where the argument is 0. Are you with me? This is essential for this function. Are you with me, class? Now, I'll give you another function after this, but for this one, you'll notice for this one, we could make this out of what? Couldn't we say this is u of t minus or plus tau over 2 minus u of t minus tau over 2? Wouldn't that be the same thing? Just look at that. Look at the first function. U of t plus tau over 2 is 0 until it hits minus tau over 2. It goes to 1, stays at 1, right? But then if I subtract from it u of t minus tau over 2, well, that one goes to 1 at t equals tau over 2, right? Wouldn't that be the same thing as the pulse function or the rect function? How many see that, class? Y'all with me? So there's a lot of ways to describe it. I can describe this probably 3 or 4 other ways. Essentially, the thing you want is this picture in your mind. If that's t, this is the pulse function, all right? Got it? I like using the piece of tau. The book uses rect. I just like the pulse, because everything I do, the journal papers and all that stuff, we always use pulse. Piece of tau. For tau's weight. So what does this one look like? Help me now. Don't answer yet. Just think about it. What would this one look like? P tau of t minus 5. And let's make it p sub, not 5, make it 6, pardon me, and make this 4. So what does that function look like versus t? Think about it for a second. The width is always the subscript, 4, right? That's the width. Where is it centered? Where the argument is 0, right? Where t minus 6 is 0, which is? T is 6. So you go to 6, right? You got to have a width of 4, so you go 2 below, which is going to be 4, 2 above, which is going to be 8. And then you put it in with a height of 1. Got it? Are you with me? So that's, then you could put rect also of t over, or of t minus 6 over 4, right? Because here's how it would look with a rect function. This would be RECT, right? Then it would be t minus 6 over 4. The 4 is not a divisor. You're not dividing that by it. It's saying that the width is 4. Understand, class? Everybody? All right, just stay sharp here, because this stuff can get really confusing. All right, this is still, it's still in the continuous time domain. All right. I'll get the energy and power in a second, but I'm looking for some exercises that will tell me if you understand. It'll tell you if you understand. The simple one. Let me give you one more function, because this one will help you. The book doesn't give you this one explicitly yet, but this one's important. And I want you to write this down and use it. All right, that pulse function is useful. This is called a triangle function. So use this symbol for the triangle function. Here's what this is. And this is the symbol for this, the triangle function T of tau. It's just a triangle. You'll notice the width itself is what? The width is tau. Y'all follow me? But now instead of being a square well or something square, now it's tapered up and down. And there's a lot of ways of describing this mathematically. Probably the most common one is this. It's simply 1 minus t, 1 minus t over, 1 minus 2t over tau, 2t over tau, pardon me. And I got to put the t with an absolute value. So it's 2 times absolute value of t over tau times a pulse of width tau. Now think about that for a second. I'm trying to make this simple. I like drawing a picture. That sticks with you. Now think about this for a second. This function has 0 value when it's minus t over tau, right? So if t is minus t over tau, or tau over 2, you put tau over 2 there, it gets an absolute value, right? You get tau over tau, or 1 minus 1 is 0. Do you all see that? It starts at 0. What's the value of this function right here when t is 0? Well, it's just 1, isn't it? Take a look. You all see that? Can you all see that right? Isn't that right? Because if t is 0, you really just got 1 times p, the pulse function, right? And you'll notice it goes back to 0 at tau over 2, doesn't it? When t is tau over 2, I have tau over 2 times 2, or tau divided by tau is 1. 1 minus 1 is 0. Do you understand that? The pulse, p tau of t, makes sure it's only got a value that's non-zero between minus tau over 2 and tau over 2. Are you with me? That's a triangle function. We're going to use that one. Write it down. The book uses this definition all the time. And they won't even use this to put the rect in there. That is just awkward. This is much easier to deal with right there. Understand, class? And this is the one I like. All right? Got it? So now what we have to do is describe, with the functions we know, things that aren't so easy to, you might say, things that have an odd shape. Let me show you a few of them. How am I going to describe this? I want you to think about it. Just think about it for a second. If I was to describe this function, there's a lot of ways, by the way. Say this value is 1, this is 2, this occurs at minus 1, this is plus 1. So the height is 2 here, it's 1 here. How would you describe this function? Call it f of t. Lots of ways. There's not one single way. Anybody got it? Want to take a shot at this? Always think about one thing. Forget the little things that are bitten out of it. Start with a basic shape that encompasses everything. You all see that? Looks like a u of t function of width, what, 4, of height 2? How many see that? Now go ahead. You're right. Go.
Okay. I was going to say use 2 times the pulse of 4.
All right, hold on. You're right. So it's 2 times a pulse of width 4 with argument t, right?
Yeah.
Now how do you take the bite out of it?
You'd subtract a
He's right. This is
pulse
one
function of width 2.
Right, now minus pulse with 2 of t. Do you all see that? That would do it, wouldn't it? How many see that? I could do it another way. There's probably an infinite number of ways, though I'm not a mathematician, So I'm not going to take that challenge from somebody who is to show me it's got a finite, innumerable number of possibilities. Look, I can just say I start here. I'm going to start with 2 times u of t plus 2. Wouldn't that start it up there? And then I'd subtract another u of t plus 1 back down here. Then here I'm going to add a u of t minus 1. And then here I'm going to subtract a 2 times u of t minus 2. And that would do it too. Do you all see that? So u of t's could be used to describe that. How many see this? Could do it another way. This is a little more problematic, but I could do it with integrations of delta functions. I could say it's the integral of 2 times delta of t plus 2, right, dt, and I could keep doing it with delta functions. And I could do it with derivatives of ramp functions. And I could probably drive you nuts with all the other possibilities. But the thing is, there is no one singular description mathematically of that. There's only one singular picture of it. There's only one picture that represents what's going on. Got it, class? Remember that. So in the answers in the book, if they don't match your description, yours is probably right, as long as the picture it draws is the same. Okay? Because they might say, well, the way I describe that is that way. I don't describe it with u of t's. Don't worry about it. Ready for another one? See who gets this one. It's a good one. And I haven't started with some of the more troublesome things yet. I'm just trying to get you guys to start thinking in terms of descriptions. Now, this is basically hardcore analysis. We're not into synthesis yet. We're analyzing things. Synthesis is a lot different. So, how do I go ahead and describe this function? Not the same guy. So it's got a height of 2 here and here. Now, in terms of the functional forms that we thought about, this is my f of t now. How do I do it? A lot of, not you, by the way. You get one shot and one class unless I feel otherwise. Anybody? Think about the basic functions. What did I say? Find one that captures everything. Anybody got a function that would? Well, those are the two we're going to use. Think about what encompasses this. Anyone? What's the height? 2, right? What's the width? 4, right? So how about we start with simply 2 times a pulse of width 4 of t. All right? Now that's what? That's this, isn't it? What do I need to do with that? I take a bite out of it, don't I? Now I've got to bite the triangle out, right? But the triangle has a height of 2, doesn't it, class? Not 1. So now I'm going to subtract from that minus 2 times the triangle waveform of width 4 of t. Do you all see that? I'm going to keep going with it. How many see that right there? You got it? Next. How do you describe this function? Is that rain?
Yes.
That's unfortunate. I don't have enough problem. Think about it. Height starts at 4 of height 2, ends at 8 of height 2, comes down like this to 1 at 6. Very similar to what we just did, a little difference, right? Couple of different things. What's the biggest difference? The shift in where things start and stop, right? It's not centered at the origin anymore, correct, class? We can always deal with that by an offset. So if you took this waveform right here, and we wanted to shift it out to have a center at 6, we would just have t minus 6 here and t minus 6 here. Do you understand that, class? Are you with me? What's the other difference? It only goes down to 1 here, not 0, right? Therefore, this bite here wouldn't have a 2, but a 1. Do you agree with me, class? So I could describe this function, think about that, as this function, my f of t here, as 2 pulse of 4 of t minus 6, right? Minus what? Triangle function of width 4, right? Of t minus 6. Wouldn't that do it, class? Please take a look at it. How many agree? That's it? And we can keep going nuts about this stuff. All right? And we will. The book has a lot of problems. Does anybody have this book right now? Anybody? You got it? Anybody have it with you here? You got it here. Here's where the fun begins. Now, so many fun functions to describe. He's actually pretty cool about it. I gave you some homework already if you look online. Did you all see that? On OneNote? Make sure you can see it. I gave you some homework. I'm going to tell you, I'm going to get through the symmetry in a second, but these are the most important parts. If you look at page 27 in your book, and then there's problem 123. If you do 121 and 123, and I think I give you the solutions, and you understand how to do them, you're in good shape with this functional business, all right? I'm going to mention a few other things before I deal with energy. There's a lot of, let me do one other thing too, because I hope this is all makes sense to you the way we went about it. I'm trying to make sure that you get a picture in your mind of what these functions look like. That way you will retain it. A lot of mathematical jargon doesn't work, just mathematical statements, but this does. So the next thing I'm going to do is something that's commonly done. Look. And it's take a known function and modify the actual argument in a way that will change its description. And I'll show you what I'm talking about. And I got to find. All right. This is 122. What he says is generating plots for this. He has some x1 of t equal to 5 times the ramp function of t plus 2. That's a ramp function. Minus 5, I think it's 5, times r of t. All right, I'm going to redo with a ramp function. So work with me. First, the ramp function itself, r of t, looks like this. Right, class? All right, now take a look at this. What does r of t plus 2 look like? Where does it start? At what? T equals minus 2, right? So it shifts this all down. So this would be r of t plus 2 right here. It would start at minus 2 and it would look like this. You agree with me? And what does that 5 do? Increases the slope. Instead of having the slope of 1, now it's 5 to 1. Correct, class? So I could draw that first one like this. Come down to minus 2. And now I have basically this. If I go over 2, I go up 10, don't I? So if I have 5 r of t plus 2, it's doing this, kind of, right? You agree with me? Now what happens next? When t is equal to 0, right, this ramp kicks in, correct? It also has a slope of 5, correct? You'll notice this is canceling the growth rate of that. Think about it. But it really looks like, I'm going to draw it there in a second, it really looks like this. There's two things. When I start at minus 2 here, this is 0. it looks like this function is doing this. Oops, excuse me. Let me really show you. It's doing this. And that function right here turns on. And that function is doing, excuse me, same slope, this, right? Isn't that right? How many see that? Add them together. Well, it goes up to here, and at this point, all the growth is canceled by this. Do you all see that? So it's level. So it just stays 10. You all see that, class? You can write it out mathematically and prove it to yourself. What I often see is this, though, on tests. See, it goes up and then 0. Because they think this ramp function kills everything. But it doesn't kill everything. It kills the growth rate. There's no longer a growth rate. It stops. So whatever that value is, 10, that's where it stays forevermore. Understand that, class? Got me? Y'all see it? All right, I'm making sure. That one gets changed.
Can you say it again?
What?
Can you say it again?
Yeah, if you just add these two together, right? If you added these two together, this one is described as what? That's really what? Isn't that t plus 2? Think about the mathematical description for r of t. It's just t times p, t times u of t, right? So it's going to be r of t plus 2 u of t, right? And then it's going to be minus what? T times u of t. And this whole thing is multiplied by 5, isn't it? And that's that function there, right? That's the ramp. Now look at this. If you look at this, take it for t greater than 0. Anything greater than 0. Or break this down right here. Now I have this is 5 times the quantity, t u of t, correct? T times, u of t plus 2, pardon me. U of t plus 2, right here, plus 2 times u of t plus 2 minus t times u of t. That's it. Now I want you to see one thing. This 2u of t plus 2, once t is greater than minus 2, it stays forever. Do you all see that? Everybody? But what happens when t is equal to or greater than 0, then this, which is going to be t times, really u of t just is 1 or 0, right? When it's greater than minus 2, this is just t, isn't it? T minus, well, when t is greater than 0, this one turns on, right? T minus t is 0, correct? So you're left with just 2 times 5 or 10. You all see that, class? Come on. It really isn't that bad if you just think about it. These are things that are increasing or decreasing at a certain rate. When they're canceling each other, it means nothing changes, but whatever is there, the residual maintains itself, right? It's going to stay there. Are you with me, class? It should be very evident to everybody. Okay. So what I'm getting at is this is what this function looks like. Stays there. Okay? That's a tricky one, though. How long is this rain going to last?
Oh,
I got a meeting. It's going to be a fun, wet meeting. All right. Now, a couple other things I'm going to go over with you. I'm going to finish with energy. A lot of this stuff you know. How many have heard of even and odd functions? All right. If we talk about an even function, this is only basically information items at this point. But if I talk about even functions, what do I mean? An even function is what? Mathematically, it means what? F of t is equal to f of minus t. Right? That's even. What does it really mean? I like pictures. An even function is something that if I come, and this is t here, and I go at 0, if I have anything over here, so I have something, if I took this axis and flipped it around and looked this way, it would look the same. That's an even function. An example of an even function is cosine of theta, or cosine of t. If you had cosine of, say, t here, then what does a cosine of t look like, right? This would be a value of pi over 2 minus pi over 2, and it does this, doesn't it, class? That's cosine, it's even. Flip around the axis. That's an even function. There's a lot of examples of even functions. Absolute value of t is an even function. But what's an odd function? Anyone?
F of t equals negative f negative
That's
t.
exactly it. F of t is equal to minus f of minus t. It's something that has odd symmetry as you take the value at f of t, and the value at f of minus t would be that value only with a negative sign. So an example of an odd function would be this, a straight line. If this is f of t here and you got a straight line, that is got odd symmetry. Another example is sine of t. When you think about the sine of t here, it does this, doesn't it? F of t, say at pi over 2, is 1. And f of minus t, if the argument's pi over 2, f of minus pi over 2 is minus 1, isn't it? So sine would have odd symmetry. These are just ways of designating functions, but later we'll see these properties are very useful for analyzing systems. Right now, it's just getting your feet wet with the terminology. And I don't spend a lot of time on that because most of you have had that in mathematics. You've had it in one of your math classes, and I'm not sure which one. So next we talked about energy. Power and energy. I think you've all had power and energy explained to you in your physics courses as well as in your circuits courses, haven't you? Remember, when you talk about power and energy, really, energy, and we'll use the symbol E, and this is for energy. Energy, capital E. Sometimes they're going to have W sub E in physics, because work and energy are the same thing. Energy is always going to be what? Well, it's the integral from minus infinity to some point t of the power p of t dt. So if you integrate power in time, you get the energy. Now, the easiest way for me to help you understand this is getting to what we're talking about really, and that's applying all this theory to electrical circuitry. So let's talk about something real where we're going to calculate both power and energy. Work with me on this, guys. So I'm going to have a voltage source here. And this voltage source is going to have the value 5 times e to the minus 2t u of t. So it's a voltage here that's going to decay. That's volts, by the way. I didn't put it down. It's going to decay exponentially. And it's only going to have values for t greater than 0. Follow me? Now I'm going to stick that into a circuit. And I'm going to make it an easy circuit. A circuit with a resistor of a value of 2 ohms. So how much power is being dissipated by that resistor at any point in time? What is electrical power if you have a circuit like this, according to Dr. David Irwin and whoever you have? And if he was here, he would riddle you.
I squared R.
Sure, it could be I squared of R. I squared what? I of t squared times R. Or it could be what? I of t times v of t. All these are acceptable, right? Or it could be v of t. Now do this one thing. Put a magnitude there. Make sure it's magnitude of I of t, and I have a reason for saying it. Magnitude of v of t squared over r, correct? All of these are correct. Do you agree with me? The reason I'm putting a magnitude is that this is a complex number, and this book does use complex numbers in the time domain, which I dislike, but he does. He chooses to do that. Then you need to take the magnitude of the complex number and square it. So for this particular case, v of t squared would be what? 5 e to the minus 2t u of t squared would be 25, right? Times e to the minus, help me? 4t, very important. Minus 4t u of t divided by r, which was 2. So that means the actual power is going to be 12.5 e to the minus 4t u of t. And power in this case would be watts. If that's volts, then that's ohms. Correct, class? Now, how much energy would be absorbed or dissipated by that resistor for all time? If we allowed this event to go on forever, how much would be dissipated? What would we have to do? To calculate the energy, what would we do? Class? Technically, we'd integrate from minus infinity to infinity, correct? If it's an energy signal, it would have a finite value of the actual power, which is 12.5 times e to the minus 4t, right? dt, and it's times u of t, so to get rid of the u of t business, I'll just start it at 0. Do you agree with me? Integrate power, you get energy, correct? What's that going to be? $12.5 integrate e to the minus 4t. What do you get? Isn't it minus what? 4, right? Minus 1 over minus 4, correct? Or minus on top. Times what? E to the minus 4t, right? Evaluated from 0 to infinity. Correct, class? Here's what I like doing. I want you to pay attention to this. When I get to this point, what I do normally is this. I switch these limits and get rid of that negative sign. Do y'all see that? So if I get rid of that negative sign, this becomes infinity, and this becomes 0, correct? So what's the energy? 12.5 over 4. What's e to the minus 0? 1, correct? E to the 0 is 1, right? E to the minus 0 is 1. 1 minus, what is e to the minus 4 times infinity? E to the minus infinity is 0, correct? Minus 0. Or the energy is simply 12.5 over 4 joules. Right? And that would be energy. And that, so far, and we've basically covered the bases on the functional forms that you have to be familiar with, the way they get skewed, the way you describe functions. We've talked about odd and even symmetry, and now we've talked about also power, which he talks about. I've given you some homework. Please do the homework. I want to encourage you to get this book by next class. Now, I didn't go over the syllabus with you. You can look at it, but I'm just going to tell you what happens. You get 2 midterms and a final. The midterms are worth 25% apiece. The final is worth 30%. I give a quiz every Friday. All the quizzes averaged together will be worth 20% of your grade. I don't collect homework. I'll give you the homework and I'll give you the answers. It's a very tempting thing not to do it. If you get caught in that trap, you may flunk. And I have had more people flunk this class in my life than any other class percentage-wise. It's this particular class, I think, is more of a problem for people that aren't self-disciplined. If you're not self-disciplined, you're in a world of trouble in this class. Okay, you've got to do your homework when it's assigned. Just read the reviews online about this course. You'll see what I'm saying. It'll save your life, literally. And try as much as possible to work by yourself. But if you need to work in a group, go ahead. One other thing I'll tell you about. A little tip from me to you that I got from the guy. Years ago, I wanted to know how to study. Luckily, one of the very first courses I had was psychology in college. But the guy knew we wanted to know what to do to learn. They're all engineers and pre-meds in this class. For analytic thought, you're thinking hard, like chess, stuff like this, playing for money or something like that. You only go about 50 minutes at a time. More than that, it's diminishing returns. You'll make mistakes faster than you get correct answers. Take a 5-10 minute break. This varies a little for people, but it's basically 50 minutes. The military probably knows more about this than any group of people on earth. Then, after 5-10 minute break, come back and do it again. Keep your area free of distractions. After about 2 of these things, you need about a 30-minute break, 15 to 30-minute break, and then you can do it again. You can keep that up most of the evening. I used to do that. When you're studying, all distractions. Phones, TVs, radio, friend, girlfriend, all that stuff, get them out. The fewer the distractions, the better the outcomes, and the more you'll retain. Long-term retention happens when you're exposed to the thing over and over again. Remember that. You'll thank me if you do this. I've had people tell me this years later. They were so thankful for those things. Another thing, beware of getting jacked up on too much coffee. And I really use too much sugar. The sugar's really bad for the blood. Sugar's flying back and forth. Next thing you know, you're going to get diabetic.